Last time we proved the limit as theta goes to 0 of sine theta over theta with the squeeze theorem is equal to 1 with the squeeze theorem. And then we had a couple of corollaries from that result. And so now what we're going to do is we're just going to take a look at some examples. And we're going to do a variety of examples. Some might involve these two special trig limits, and a lot of them won't. So let's just jump right in, and we're just going to evaluate some limits involving trig functions. We're also going to have some log functions and some exponential functions in this section as well. So first of all, let's go back to simple ideas to start. If I was to ask you to evaluate the limit, let's say as x approaches 2 pi of sine of x over 6. Well, sine of 1/6 x over 6, that's going to be just a nice continuous function everywhere. So we're just going to start off with our first instinct on most limits is going to be, first, let's just try direct substitution. And so that's exactly what we're going to do. So we would have sine of 2 pi over 6, and of course that reduces to sine of pi over 3, and that should be one that we know from our unit circle. You think about what's that y coordinate that's up there at 60 degrees on your unit circle, and that is our square root of 3 over 2. So just evaluating straight away, just using direct substitution. Let's do another one. So suppose I have number 2, my limit as x approaches 1/3 of the natural log of 3x. Now, the natural log function, just an important thing to remember in general, is that log functions have to be positive. So this will come up, I'll just kind of jot it down quickly, I'll end up erasing this, but the domain of log of anything, the inside always needs to be positive or greater than 0. So, in this case, 3x needs to be greater than 0, so x would need to be greater than 0. So the function, though, itself, the natural log function, is continuous everywhere on its domain, and 1/3 is certainly in its domain, so we're not going to have any issues here. And so all we need to do, once again, is just some direct substitution. So natural log of 3 times 1/3, and I picked a really nice one because natural log of 1, I hope you remember that, that's just equal to 0. Log of any base of 1 is 0, right? Because it's asking the question e to what power is equal to 1, and that's 0. Obviously, you can, look at your calculator as well. But so, some of these we're going to start off and just handle like direct substitution. All right, so let's continue. So example number 3. Suppose we're looking at the limit as theta goes to 0 of sine squared theta over cosine theta tangent theta. So initially, I should think, well, let's just try direct substitution. However, in this case, if we were to try our direct substitution, sine of 0 is 0, 0 squared is 0. Cosine of 0 is 1, but tangent of 0 is 0. So we have this 0 over 0, which we know is an indeterminate form. And so with trig functions, first instinct should be, can I apply just any basic trig identities in order to potentially get this into a different form that I can reevaluate? So just like with our last section, a lot of times we factored in reduced or multiplied by a conjugate, or we did some sort of things along those lines. With trig functions, what you want to think about is, can you use maybe first just any, basic trig identities? All right, well, probably, the most common approach to working with trig functions and trig identities is often to take and get everything in terms of sine and cosine. So what we really have here in our denominator is going to be tangent written as sine over cosine. So now if I start to do some reducing here, again, the limits are equal. We are changing the domains of these functions, so the functions themselves are not exactly equal anymore, but their limits are equal. So at this point, I have the limit as theta goes to 0 of sine squared theta over sine of theta. And then once again, I'm going to do a little reducing. I'm going to reduce one of my factors of sine there. And so now I have just the limit as theta goes to 0 of sine of theta. Now I will evaluate. So up until now, I needed my limit notation. Now as I actually evaluate it, I will drop my limit notation. But all of this work is necessary. You can't just answer 0 because there were zeros everywhere in the original, right? 0 over 0. But you have to go through all this to get to something in this case that, as it turned out, did end up equaling 0. All right, so again, just kind of continuing to look at some examples here. Number 4, let's say that we have, we're going to do several parts on this one. So suppose we have our limit as theta goes to pi over 4 of 2 sine theta over 3 theta. I don't know why I wrote that so far over there. All right, so first instinct should be direct substitution. Here's the thing you don't want to run into. Oh, look, sine theta over theta, that equals 1. Okay, first of all, it doesn't equal 1. Its limit goes to 1, and its limit only goes to 1 if theta is going to 0. So real common mistake, and that's why I'm doing it. So here we want to do just what we did on our first few examples. Let's start by doing direct substitution. And guess what? This is fine. Sine of pi over 4 is square root of 2 over 2. And then now I have divided by 3 pi over 4. And so dividing by a fraction is multiplying by its reciprocal. And so it looks like our final answer here is going to be 4 times the square root of 2 over 3 pi. All right, now suppose I had part B. Now let's say I had the limit as theta goes to 0 of this same function, 2 sine of theta over 3 theta. Well, again, I would start and I would think about direct substitution, but I would have sine of 0 is 0 over 3 times 0, so I have 0 over 0, and that's our indeterminate form. But this is where I would say, but this one we've proven. That constant multiple, you can carry this 2/3 out in front of that limit. That's one of our properties of limits, as a constant multiple times the limit as theta goes to 0 of sine of theta over theta. And this one we have proven. That's what we did in our last video. We proved this one by good old squeeze theorem. And so this was equal to 1. And so we have 2/3 times 1, and that, of course, is equal to 2/3. So that's an important distinction to make. So we will stop there and come back and look at some more examples next time.